Yes. Well, I have no control over that. So it's before the physics exam. We're going to do 2 review sessions. I'll do one Sunday afternoon, and Professor Bonifant will do one Tuesday evening. We're sort of constrained by when we can get rooms large enough to hold more than 100 people. So the review session that we're going to do on the Tuesday before, I think it's at, what is the class slot that ends at 8 something? 6:50, right? Yeah. So this is at 6:50. And I still need to get in time for this one, but it's Sunday afternoon. Yeah. Yes, there are, well, no, there are classes. There are no other exams. If you have a class at that time, you need to make arrangements not to go. So this time was announced when you, this time and the time of the other one was scheduled last January. So even before I knew I was teaching this class, we have no control over that. The registrar picks it. Yeah. The exam? Oh, the review. I could review the Sunday. I could do the Sunday one. I'm not so sure about the Tuesday one. I will try to review video the Sunday one. It probably won't be up until Tuesday or so, maybe Monday. Do people watch the videos?
Yeah.
Okay. Once in a while, it's like, geez, it's him again. All right, we're done. Okay. For those of you that are using laptops or phones for clickers, I know that networking in this room is a little problematic. They broke WolfieNet Secure, and then they tried to fix it. I'm sure you got messages about it. It kind of sort of works if you force it. Sometimes it works, sometimes it doesn't. You could also try WolfieNet Guest. I don't think WolfieNet Open exists in this room. It's supposed to, but it doesn't. So, anyway. Okay, so let's go on from where we were. So, what we were talking about was this idea of improper integrals, which is if we have either an unbounded domain, so for example, so we can define, so I said this last time, the integral from anything to infinity of some function to just be the limit as the upper bound goes to infinity of that function. This is just saying, if I want to integrate some function that stretches off that way, I just cut it off further and further out, and I send the cutoff off to infinity. And so if this limit exists, and then we say it converges. And if not, we say it diverges. Okay, so I did an example of that last time. At the end of the class, I integrated e to the minus x from 0 to infinity. The answer is 1. Everybody okay with this idea? It's relatively straightforward. So, let's do one. In fact, I'm going to make this be a quicker question. So the integral from 0 to infinity of 1 1 plus x squared dx is A, divergent, B, 1, C, pi, D, pi over 2. Start that A, B, C, D, E, no, A. So most of you got it right. Well, half of you. So 31% think this is the right answer. 17% think this is the right answer. Whatever this number is that's left over, 50% think this is the right answer, and this must be something small. I don't know. So, this is supposed to be relatively easy, because what we do is we can do this integral. I hope you all know this integral. This is the arctangent. So this is, take something going to infinity, of the arctangent, the value of x, evaluated from 0 to m, which is the arctangent of m, take the limit as m gets big, minus the arctangent of 0. So the inverse tangent of 0 is 0. And the inverse tangent, if we think of the graph of the inverse tangent, the limit's here on pi over 2. Because the tangent of pi over 2 is infinite. So this is pi over 2 minus 0. So the answer is pi over 2. Okay? So this is, I thought, fairly easy, but I guess not so much for you. It took a long time. I don't know why it took a long time, but okay. So half of you knew the right answer, and a lot of you thought it was divergent. Okay. Let's try another one. So let's try the integral from 1 to infinity of 1 over x dx. And so I'm going to ask you again. So A, this is divergent. B, this is 1. C, this is log 2. D, this is E squared. And E, convergent, but not one of the above. Okay. How many people need more time? Nobody? Okay. You need more time? Okay. I'll give you 30 seconds. Done now. Copy them both. So this time, most of you got it wrong. So a lot of people, very few people said this one. So less than 5% for this, this, and this. So now it's between these two. So how do we do this? We do this just the same way. Well, yeah, the limit as m goes to infinity. What's the integral of 1 over x? Right, the log. So it's the log of m minus the log of 1. And we have to take, so the log of 1, still 0. This is 0. And now we need to know what's the limit as m goes to infinity of the log. What does the graph of the log look like? It goes like that. It doesn't have a limit, it grows forever. The log is just what exponent you need to raise e to get some big number. So you take your big number and you raise e to a big exponent. So this is infinity minus 0. So this does not exist, so this diverges. 47% of you thought, no, sorry, 41% of you thought it diverged, and 47% thought it converged. So at least you weren't fooled by my distractors. Okay, one more. You should get the hang of this by now. So same choices. I didn't start it, so. All right, I'm going to stop this now. Okay, so, oh well, some people came in at the last moment and got it wrong, but before it was like 85% right answer. Now it went down to 63 because a bunch of people either changed their mind or got it incorrect. So anyway, let's just do this problem. So the integral of 1 over x squared is minus 1 over x, right? Because this is x to the minus 2. Add 1 to the power, you get x to the minus 1. And I have to divide by the power. So this is this guy evaluated from 1 to n. The limit as n goes to infinity. So this is the same as minus 1 over m minus a minus 1. Limit. So as n goes to infinity, that's an infinity. 1 over m goes to 0. Minus minus 1 is plus 1. So this is plus 1. So this is the right answer. And 63% of you thought it was the right answer. And the second prize goes to this. So it's good that you know it converged, but it would be better if you knew it converged too. Okay. So these things, I think, are relatively straightforward. It's just a matter of doing an integral as before, but one of the limits you just let go to infinity. It's a little, yeah, so it's a little. So now if we have something like, let's just do this. If we have something like this where we're going on both sides, so this is saying the graph of 1 over 1 plus x squared looks kind of like a bell curve. It's not the bell curve, but it sort of looks like that. And here we're saying both sides. We can do this in two ways. One way we can notice that this is an even function, and so this is the same thing as twice the integral from 0 to infinity, 1 over 1 plus squared. We can do that because it's even. That is, the area over here is the same as the area over here. But even if it weren't an even function, we could still do this by splitting it up. Let me move my graph. By splitting it up as, say, the integral from minus infinity to pick any place, how about 0, plus the integral from 0 to infinity. And now we can do this in the same way. We take the limit as, let's say, L goes to minus infinity on this side, and N goes to plus infinity on this side. So this is the arctan 0 minus the arctan L. That's the first integral, plus the limit as M goes to infinity of the arctan M minus 0. That's it. So, anyway, this is pi over 2 plus pi over 2. Okay, so I'm saying I can do it in two ways. One way, I can notice that the function is even. Do half of the integral, start at 0, go to infinity. I just did it, it's over. It's right here. I got pi over 2, so it's twice what I got before. If this function, even if this function is not even, so I can't use this trick, I can still always split it in half. I split it at 0, I do one side, and I do the other side. Yeah. No. So even means symmetric with respect to the y-axis. Odd means symmetric with respect to 0, or it's even but it's flipped on the other side. There are certainly plenty of functions that are neither even nor odd, such as e to the x, log, most polynomials, but not all, things like that. Most functions are neither even nor odd. Just like most numbers are neither even nor odd, because you have fractions. If it's odd, you can play the same trick, you just change the sign. If the function is odd, then I can still split it, but I only have to do 1/2 of the integral, because I know the other one because it's negative. And it would be 0. Okay. So again, there's not a whole lot to these other than wrapping your head around the idea that something with an infinite domain can have a finite area. But as we see, we have several that do, and several that don't. Now, another thing that can go on is we might have an integral like let's do something like this. Now this has a little bit of an issue at 0. It's okay at 1, but it has a problem at 0. But it's the same trick. Right? The graph of 1 over the square root of x looks like this. And we're only going out to 1. So the area that we're looking at here could be infinite because it blows up here. So, but we can do the exact same trick. We just take this to be the limit as, I don't know, a goes to 0 from above of a to 1. Let me write it this way, just to x to the minus 1/2 dx. And then we can just do this integral as before. The integral of x to the minus 1/2 is well, x to the plus 1/2, but I have to divide by 2, divide by 1/2, so this is limit a goes to 0 from above of x to the plus 1/2, but then I divide by the new power, so 2 from a 1. Everyone okay with this? So then this is, I take the limit of 2 times the square root of 1 minus 2 times the square root of a, as a goes to 0, so this is 2. This piece goes to 0, and that piece goes to 2, so the answer is 2. I did it. Okay? Now, once in a while, these things can be hiding. Let me just keep this same. No, I can't do the same. Sorry. Suppose I have something like the integral from 0 to 2 of 1 over 1 minus x. Suppose I have something like that. Now this looks like it's okay. Right? So here's a wrong answer. Do the integral of 1 over x minus 1. You make a substitution, u equals x minus 1, dx equals du, so there's 1 over u, so this is a log. So this is the log of 3 minus the log of, well, it's not a log. Shoot. Minus the log of 1/2. Now that's a number. This is wrong. Why is this wrong? Right. So this is just a number, and this is wrong because when x is 1, we have trouble. Since the graph here from 1/2 to 3, so 1 over 1/2 is 2, and it blows up at 1. And then here, oh wait, sorry. It's x minus 1. So it blows up here at 1. Yeah, that's right. The graph looks like, so 1 equals. Did I get this wrong? Yes, I'm backwards. It's here. Okay. So the graph looks like this. It has a problem here at x equals 1. So we can't do it this way. Yeah. Doesn't matter, it's still wrong. Well, it's especially wrong now because we have the log of -1/2, which is even messier. So anyway, it's all wrong because it's just completely wrong. But the point that I'm trying to get at is that you can't just jump over this. And in fact, notice that the integral from 1 to 3, 1 over x minus 1 dx, so this must equal, if it exists at all, the integral from 1/2 to 1, 1 over x minus 1 dx plus the integral from 1 to 3. And here, this diverges because I didn't leave enough room. so here, okay, so this guy we can do, this is the limit as, I don't know, a goes to 1 from below of the natural log of x minus 1 evaluated from 1/2 of a plus the limit as b goes to 1 from above of the natural log of x minus 1 evaluated from b to 3. And so this is the natural log. 1/2 minus 1 is 1/2 when you take the absolute value. Minus the natural log of the limit as a goes to 1 minus the natural log of x minus 1. And this blows up. And so does this. It's the same one. That's B, that's an A. So this blows up. And so this diverges. Okay. So you have to be a little bit careful. You have to make sure that when you're integrating, your function is defined on the whole domain, and if it blows up somewhere within the domain, you have to split it there and do an improper integral as you approach that. Any question? Just you can talk. Now, sometimes, so for example, suppose that you're going to do something numerically. It's probably a good idea to know whether your integral makes sense or not before, even if you can't do the integral in this way. So one of the questions that you might ask is, does the integral exist or not? So if I have something like the integral from 0 to infinity of e to the minus x squared dx, we might want to know, does this converge or does it not converge before we try and do it numerically. This we cannot do by any means except numerically. We already know this. This is the bell curve. But we know that this makes sense. How do we know that this makes sense, even though we can't calculate it? Because I told you. So, what's the biggest this could possibly be? Why? Somebody said 1. 1 is good. Why 1? Because it's not 7 and I just keep writing 1 on the board. They're always 1. Somebody said 1. 2 people said 1. Just because you know? Oh, there you are. Yeah?
Is it because, like, the bell curve, I know it's
Well, this is not quite the bell curve. You have to divide by pi over 2. So the real one for the statistics bell curve, it's over 2 here, and then there's like a either pi over 2 or 2 over pi. So how can we? So people know this is true, but why? It's 1 over e. Okay, that's true. Okay. But if I add up a lot of things less than 1, they can add up to b. So I can add up, for example, 1, well, 1 is no bigger than 1, plus a half, plus a fourth, plus an eighth, and so on, and get to 2. Or I can add 1 plus a half, plus a third, plus a quarter, and get to infinity. So just because everything under here is less than 1 doesn't mean this is less than 1. But you have the right idea. Even though maybe you don't know that you have the right idea. So you need a hint. Someone else have an idea? Yeah. But it's a number. How can I take a derivative? Take the derivative of, and that will tell me where the critical point is. I can tell you right now the critical point is at 0. The graph of this function that's inside here looks like this. Okay, so this is not completely obvious. So if that's true, if x is bigger than 1, right? Maybe it's equal if x is 1. And we already know what the integral of this is. The integral from 1 to infinity of e to the minus x is 1. We already did that. So maybe 1 is not quite big enough. Maybe I need 2. So the idea here is we know that this graph, e to the minus x squared, eventually slips underneath e to the minus x. They cross at 1. And this guy, I mean, my scale is going off. The shaded area that we want sits underneath the area of e to the minus x. So that means that whatever this area is, it has to be less than this piece. Let me change this problem a little bit. I'm sorry, just to make it easier. So this has to be less than, or maybe equal, but not really, the integral from 1 to infinity of e to the minus x dx. And we did this last week, that this is the limit as m goes to infinity of minus e to the minus x from 1 to m, which is 1 minus 1 over m, limit to 1. So because the function here is always smaller than the function here, the integral here has to be smaller than the integral here. Even if you can't calculate it. Right? Yes? I'm going to write it down like that. So the function here is always smaller than the function here. So the integral here has to be smaller than the integral here. Right? If I have a room that's higher than a smaller room, I can fill up the taller room with more stuff than I can fill up the smaller room. So if I were to fill this room halfway full, I would have less stuff than if I filled this room all the way full. So we know that if I fill this room halfway full of those little balls that you play around in, you fill this with those little red and yellow and green balls, the volume of the balls is less than the entire volume of this room. So we can say that a little more formally. Math talk. We call this a comparison theorem. So if I have one function that's bigger than another function, And the big function, I don't care where it starts, converges and so does the little function. And it converges to something less than the big guy. Right? So if we have an upper bound that we know is some number, and we're trying to grow to infinity, we can't, because we can't get bigger than the top function. There's, oh, I can't put that up. Oh well. There is another part to this. Which says that if the little function doesn't converge, so again, I still have f of x bigger than g of x, and the integral diverges, then so does the big guy. So, if g of x is going to the moon, and you're sitting on top of g of x, guess where you're going? Right? This guy is bigger than that one. This guy goes to infinity. The area of this one is infinite. Here, that one has to be infinite.